Hello, friends. It's a beautiful afternoon in Kigali. I hope you are doing great. And today I want us to go to gravitation lesson 4. So this is gravitation lesson 4. And don't forget, this is physics 9702. Specifically, this is paper 4. And I want us to move to lesson number 4. In lesson number 4, we are going to actually concentrate on the energy in a gravitational field. Have you ever wondered what would happen or what the gravitational potential energy would be if one object and another, they are at the same level, but one is just above let's say the ocean or above a lake, and another one is just above the mountain, but the two objects are at the same level. So today I want us to look at the idea of energy in a gravitational field. So to begin with, we are so much aware that if we consider an object, say on the Earth's surface, if we consider an object, say on the Earth's surface, assuming we were considering a reference part which is actually flat, if an object is initially at position A, which is just on the surface or close to the surface of the Earth, somebody would wish to say that at position A, the potential energy of this object is equal to 0, or the gravitational potential energy of this object is equal to 0, because this person is using this Earth's surface as the reference point. But then, suppose this object is moved against gravity to a certain height. Say it has been moved through a certain distance, say a certain height h, which I will simply write as change in h, because actually later on we shall see that this gravitational potential energy is supposed to be with reference to the center of the Earth. So when I move from the surface of the Earth to a certain height, there has been just a change in distance h, because already it was at a certain height from the center of the Earth, because the field is radial and the field acts towards the center of the Earth. So by moving this mass, from this point, from the Earth's surface to a certain height h, work has been done, and from AS we saw that the work done is given by force times distance. So there has been work done against gravity, so the force is going to be equal to, because we are doing work against gravity, if the mass of the object is m, then the force, we are doing work against the weight, so this will be equal to mg times the distance moved through, which is going to be delta h. So it means the work done on the object to take it to this height will be now the energy stored in the object at that height. And therefore, this will be the gravitational potential energy, which will be equal to mg delta h. So what does that mean? When I move an object from the Earth's surface, or when I lift an object from the ground to a certain height, I am increasing the gravitational potential energy. Why am I increasing the gravitational potential energy? I know that the force between this mass that I am moving from the certain height from the Earth's surface to a certain height, the force between this object and the Earth is attractive. In other words, the Earth attracts or pulls every object towards the center. So by moving it against gravity, I am adding energy to the object. So there is a gain in potential energy. So the higher you lift this object, the more work is done. That means the greater the gravitational potential energy possessed by this object. So when an object changes its position relative to the Earth's surface, there is a change in potential energy. So what I have just quoted here, because there's a change in the height h, then what I've just quoted here is actually a change in potential energy. I'll write this as delta EP, where E subscript P is potential energy, is equal to mg times the change in height. Now note that here G is constant when you are very close to the Earth's surface. But we know that when you move so many kilometers away from the Earth's surface, G is no longer the same. It also varies. In fact, when you are so many kilometers, when the mass is so many kilometers away from the Earth's surface, G becomes smaller because we saw that G varies as the inverse square of its distance from the surface. But of course, close to the Earth's surface, the field lines are almost parallel to each other, where G is considered to be constant. So if the body moves just a few meters or if a small distance above the Earth's surface, G is still considered to be constant. Therefore, this expression is valid. But if we move or the object moves several kilometers away from the Earth's surface, so many kilometers away from the Earth's surface, then we cannot use this expression in the first place because G will actually be changing. In fact, G will decrease as the body moves away from the Earth's surface. G decreases. Every time we use this expression, we are assuming that the gravitational field strength is constant. Therefore, this equation will only be applied when the object is close to the planet, or when the object is close to the surface of the planet, or when the change in height is relatively smaller. For objects in space, I really don't think this expression will be applicable as we saw it in AS. I want you to look at another scenario. Here we have looked at one object. Let's consider two objects. This object, one object is above, or both of them are above the Earth's surface, but one object is here and another object is at this point here. So this is object A and this is object B. These two objects are at the same level. That means they are at the same height from the Earth's surface. Therefore, they have the same gravitational potential energy. So the A and B will have the same gravitational potential energy with the Earth's surface as the reference point. But then, let's try to modify this further. Let us assume now this is the Earth's surface because the Earth is not always flat throughout. So we have now this as the Earth's surface because some point it could be hilly, some points could be mountainous. And object A is here and object B is here. Even if these two objects have the same mass, this is A and this is B, and even if these two objects are at the same horizontal level, somebody would say that, okay, with reference to the Earth's surface, this one has a higher gravitational potential energy because of its h from the Earth's surface. Another person would say, this one has a smaller gravitational potential energy if this is its height from the Earth's surface. These two people could be true. These two people could be correct. But suppose the two objects are on the same surface. They are on the Earth's surface. Let's say now A is brought here to the surface and B is brought here to the surface. What shall we say? Shall we say that still B has a higher gravitational potential energy than A? What shall we be considering when both objects are on the Earth's surface? So it becomes quite confusing whenever we use the Earth's surface as the reference point. Therefore, scientifically we can say it is not possible to place an absolute. It is not possible to place an absolute value. It is not possible to place an absolute value on the potential energy of any object when h or whenever the height is measured relative to the surface of the Earth. It is not possible. We can't make a conclusion on the potential energy of two objects when the surface of the Earth is the reference point. Because will you say that this object has a higher potential energy than this one, yet both of them are on the same Earth's surface? Because the Earth, it is no guarantee that the Earth's surface is supposed to be flat throughout. Would you say that this one has a smaller potential energy than this one? By the way, if we refer to the Earth as the reference point, This object here and this object here will both have potential energy 0 if the Earth is the reference point, because both objects are resting on the Earth's surface. So we are saying that two similar objects placed at the top and the bottom of a hill may have different values. They may have different values of potential energy. But if we consider the ground or the Earth's surface as the reference point, both objects have 0 potential energy. Absolute values of potential energy cannot be measured relative to the Earth's surface. When I say something is absolute, it means it is agreed upon in every situation. But here we cannot agree on the potential energy of these two objects in all situations when the Earth's surface is the reference point. Somebody will say this one has a higher potential energy than this one. For that person, he would be using this one as the reference, this position as the reference point. Yet another one will say this one and this one have 0 potential energy because both of them are on the Earth's surface. So we say in such situations, we cannot place an absolute value on potential energy when the Earth's surface is the reference point. Then what should we do? Something has to be done. Something has to be done. And what should be done? Absolute values of potential energy must be measured relative to the same point which never changes. And we shall define a new point of reference as infinity. We shall define a new point of reference as infinity. By the way, infinity is the same for all objects. You and me have the same infinity. Because what happens at infinity? One, if two objects are at infinity, or if one object is at infinity with respect to the Earth, for example, when it is at infinity, it experiences no gravitational force by the Earth. So the gravitational field strength is negligible at infinity. And if it is at infinity, by the way, the potential energy depends on this force. If it is at infinity where there is no force, then the potential energy at infinity is going to be defined as 0. And it will be the same for all objects because infinity is the same for all objects. So I am saying for absolute values, which will be acceptable in all situations, the reference point should not be varying. It should be the same. And a new reference point, which we are going to call infinity, has to be defined. When an object is at infinity relative to another, it means the gravitational field strength of one object cannot interfere with another object. Therefore, the potential energy when there is no force acting on an object due to another mass is actually too small and negligible, so we consider it to be 0. So I am saying we have defined a new position or a new reference point rather than using the Earth's surface, which is not flat throughout. And this point is infinity, and we are saying that potential energy at infinity is equal to 0. Potential energy at infinity is defined to be 0, and it will be the same for all objects, irrespective of their distance from the Earth's surface. Potential energy at infinity is going to be 0. So this is what I have actually been talking about. This is what I have actually been talking about. I think I need to erase this. So we have said if you lift an object from the ground, there is an increase in gravitational potential energy, and the higher you lift it, the more work you do on it. Therefore, the greater the potential energy. That is very true. And we have also said that when an object changes its position relative to the Earth, there is a change in potential energy, and the potential energy is given by this, where delta H is the change in height. But I mentioned here we are at a small value of h, where g is approximately the constant. Close to the Earth's surface, where g is approximately constant. But if we look at now two positions of the cars below, One is at this level here, another one is at that level there. It becomes quite confusing to say or suggest which one has a higher gravitational potential energy. So it depends on what you have considered as the reference point. If somebody says this is the reference point, then this one has a higher potential energy than this one. But if somebody says the Earth's surface is the reference point, then if the two cars are on the Earth's surface, then they both have the same potential energy, which in this case will be zero because they have not left the surface of the Earth. So the car at the top of the hill can be said to have more potential energy than the one at the bottom, if the bottom part is the reference point. But if we consider the Earth's surface as the reference point, we are saying relative to the Earth's surface or relative to the ground, both of these cars will have zero potential energy. Both of those cars will have zero potential energy. What does this mean? We can therefore not place absolute values on potential energy when the Earth is the reference point, because there is some contradiction, there is some disagreement. That's why we are saying we can't place absolute values on potential energy by relying on the Earth's surface as the reference point. And a new reference point had to be redefined. So this is what I am actually emphasizing. In my explanation, so this we have seen all this, and in my explanation I have mentioned and said it is not possible to place an absolute value. It is not possible to place an absolute value on the potential energy of an object, especially when h is measured relative to the Earth's surface. Then when should we have absolute values? Absolute values of potential energy are measured relative to infinity. In this context, infinity means a distance from the Earth where its gravitational field strength is so small as to be negligible. So at infinity, because at infinity the gravitational field strength is so small, it means the gravitational field is approximately zero. And if the gravitational field strength at infinity is approximately zero, then a mass at infinity experiences almost no force. Therefore, the gravitational potential energy or the potential energy at infinity is approximately zero. Go back to ideal gases where we said if the force of the intermolecular forces between two molecules is negligible, then the potential energy is zero. So if a mass is at an infinite distance from another mass, its potential energy is going to be zero. So every time we use the equation EP is equal to mg delta H, which assumptions are we always making? Every time we use this equation, we are assuming that the object's gravitational potential energy is zero on the Earth's surface. By the way, that is also wrong to think that objects on the Earth's surface have gravitational potential energy zero. That is also wrong. So every time we calculate, we, we are actually finding a change in height. Therefore, we are finding a change in potential energy rather than potential energy. When you move an object from the Earth's surface, you're not moving it from a point where potential energy is zero. Not at all. However, you move it to a certain height where the change in height will indicate a change in potential energy. So it is wrong to use mgh. Instead, we would rather use mg delta h, where delta h means you are moving from the surface of the Earth to another point where the surface of the Earth is not actually where the potential energy is zero. We are later on going to see that the center of the Earth is actually the reference, it would have been the most significant reference point. But since we take observations from the Earth's surface, then we cannot use the center of the Earth as the reference point. So This equation here is fine for practical purposes and especially in AS, but not, for example, if we are considering objects moving through space where they are far away from the Earth. Remember, in space, g is not going to be constant because g varies as the inverse square of the distance from the Earth's surface. Yet when we are using this equation here, we are assuming that g is actually constant. So, if we lift an object at a greater height, if we lift an object to a greater height, the value of g is actually going to be decreasing. This means we would need to take this into account when we are calculating the gravitational potential energy. So how do you take into account when you are calculating gravitational potential energy that g decreases when you move infinitely far away from the Earth's surface when you are using this expression? So you cannot rely on the Earth's surface as a reference point because when you are in space, g is going to vary as the inverse square. So this expression cannot be used when you are far away from the Earth's surface where the gravitational field strength decreases due to the Earth. So I am saying that this expression EP is equal to mg delta H will only be true when we are very close to the Earth's surface, since the field is considered to be uniform near the surface of the Earth. So I am saying, and I'm saying this in bold, do not use this expression here, mg delta H, for objects out in space. We only use this expression for objects that are close to the Earth's surface. Do not be tempted to use it for objects out in space, far away from the Earth's surface. Because in this case, we have said, since the Earth is not always flat, it means another reference point is going to be redefined, which is the same for all objects. Infinity is the same for all objects because they behave the same way. At infinity, they will have zero potential energy. Therefore, the reference point can be redefined. So let's redefine a reference point. So I said for this reason, we need to set up a different way of thinking about gravitational potential. We are going to see what we mean by gravitational potential. But before doing this, let's try to redefine a reference point rather than the Earth's surface. So let us redefine a new reference point that we have already mentioned. So other than using the Earth's surface as a reference point, which the Earth is not always very flat, a new reference point that I've mentioned is infinity. So let us start by picturing or observing an object at infinity. Note that infinity can be different. I mean, infinity is the distance between two masses where one mass cannot experience a gravitational field due to another mass. Then those two objects or one mass can be said to be at infinity relative to another. So when an object is at infinity, we are saying that the gravitational field strength is so small and it can be neglected. So, and if the gravitational field strength G is neglected approximately zero, then it means the force of attraction on that object due to the other mass is also zero, which makes the potential energy to be approximately zero. So we are saying the potential or the gravitational potential energy or potential energy at infinity is going to be zero. So the more convenient way of defining the zero of gravitational potential energy is by relying on infinity rather than using the surface of the Earth. So this is a more convenient way of defining the zero of gravitational potential energy than using the surface of the Earth. So we now know that at infinity, the gravitational field strength is almost zero. And if it is zero, the force due to the gravitational pull is approximately zero. And if the force is zero, then the potential energy or the potential for an object at infinity is defined to be zero. Now, let us picture moving a mass from infinity now. We now know that at infinity, potential energy is zero, or gravitational potential energy is zero. So we have the Earth's surface, we have the Earth somewhere here. Let this be the Earth. And we are going to assume that an object is coming from infinity. I'll use dotted lines to go to infinity. I'm now moving from infinity. I think you see me moving from infinity. Now I have moved from infinity. Maybe let me use this to be in infinity. So this is at infinity, where potential energy or potential is zero. I have now moved an object from infinity to a point where the gravitational field strength is not zero, but when it is at a distance, r from the surface of the Earth, this is now where our test mass, which was at infinity, now experiences a force. What work has been done to move an object from infinity to this point? That will now be our task here. What work has been done to move an object from infinity to that point? Before we establish that work, we are going to picture moving a mass from infinity to this point. So we may want to know the gravitational potential energy at this point. Note that at infinity, the gravitational potential energy is zero. But when you move an object towards the Earth's surface, you are bringing it in the same direction as the gravitational field. When you lift an object from the Earth's surface, you are taking it away, you are moving it against the gravitational pull, which is downwards. So here you are doing work onto the object. The object is gaining gravitational potential energy when you are moving it against gravity. So when we move the object against the force of attraction, because the force between two masses is always attractive, when I move it against the force of attraction, it gains gravitational potential energy. So if I move it up to infinity, it has gained gravitational potential energy, which is zero at infinity. That means before I reach the infinity, it must have been less than zero. That logic is very easy to understand. When you lift an object from the Earth's surface, you are moving it against gravity. It gains energy. Work is done, and that work is added to the object. Its gravitational potential energy increases. If you were to move it from the Earth's surface up to infinity, it means its gravitational potential energy increases up to infinity, and at infinity it is zero. So it was increasing up to zero. How do we increase up to zero? It is by moving through negative values. So it means elsewhere less than infinity, the gravitational potential energy will be negative. When I move this object to infinity, the gravitational potential energy increases and it becomes zero at infinity. It means when I bring it closer than infinity, the gravitational potential energy must be decreasing, or it should be a value less than a value less than zero, which should be negative. At this point, you must have noted that every time we talk about gravitational potential or gravitational potential energy, the values involved will always be negative. One, because potential at infinity has been defined to be zero. Two, the force between two masses is always attractive. That means when I move the object from infinity to the Earth's surface, the object is losing energy. Work is done by the object. So the object loses work, or the object loses energy. So the gravitational potential energy it remains with must be less than zero. So it will be negative. And by the way, if I am moving a mass from infinity to a point in the gravitational field, I'm transferring energy to that. Actually, the object is losing energy. When I move it from this point P, taking it to infinity, I'm transferring energy to it. So moving it to infinity, the gravitational potential energy increases. Moving it from infinity closer to the Earth's surface, the gravitational potential energy decreases. So in summary, this is what I'm saying. That if we picture moving the mass to a point where we want to know its gravitational potential energy, As with lifting an object from the ground, we determine the work done to move the mass from infinity to that point. Just like we determined the work done in lifting an object from the Earth's surface to a certain height. We can also determine the work done to move the mass from infinity to that point. But remember, when you are moving it from infinity where the gravitational field strength is 0, you are bringing it to a point where the gravitational field strength is higher. So it means the object is losing energy. It only gains energy when you take it to a further distance. Somebody may also recall from one of the lessons that the gravitational field strength I mentioned somewhere can sometimes be quoted as negative Gm over r squared. This negative was indicating that the force between two masses is always attractive. So the work done on it is equal to the energy transferred to it. Its gravitational potential energy is the work done. And that is how we can determine the gravitational potential energy of a particular mass. So we always picture moving a mass from a certain point, from infinity to a certain point. The work we do in moving it from infinity to a certain point is the energy transferred to that mass, which is going to be the gravitational potential energy. In summary, in summary, all objects at infinity have the same potential energy, which is 0. All objects at infinity will have the same potential energy, which is 0. That's why we said infinity is a better reference point, because infinity gives the same potential energy, which is 0 for all objects. If there is any object which is closer than infinity, then it has a negative amount of potential energy, since it would need to acquire energy in order to reach infinity and have 0 energy. If it is acquiring energy in order to reach infinity where potential energy is 0, then it should be acquiring negative values. Therefore, any object closer than infinity should have negative values. And I have also mentioned that the expression, which is EP is equal to mg delta h, will only work for objects very close to the Earth's surface where g is considered approximately constant. I still insist we cannot use this expression for objects in space. In A level, this expression will be very rare in gravitation. So another expression will always be adopted. We shall adopt another expression which takes into consideration that the Earth's surface is not always flat, so it's not a better reference point for energies. To begin with, let's talk about gravitational potential. Let's talk about gravitational potential. I think potential relates to energy, and we have said if we consider the Earth as a certain, if we consider the Earth somewhere, and we imagine moving a unit mass, this time I will consider unit mass, that is a mass of 1 kilogram, from infinity. Of course, when it is at infinity, the force due to the Earth at infinity, the force is 0 because the gravitational field strength at infinity is almost negligible. That means the potential energy for this object at infinity is 0. Now remember, it is a unit mass. Now when I move it to closer to the Earth's surface, and it is at a distance, say r from the center of the Earth. So I have brought my 1 kilogram in a region where it experiences the Earth's gravitational field. At this point, I know I can find the gravitational field strength, G. At this point, I know there is a force due to the gravitational field. Then there is a potential energy here, which should be less than 0. Therefore, this potential energy here is going to be negative. The work done in moving a unit mass or a mass of 1 kilogram from infinity to this point here is going to be called the gravitational potential. So we are saying gravitational potential is the work done in moving a unit test mass, from infinity to this point. The work done in moving a unit test mass from infinity to that point. So this work done will be surprising. So the gravitational potential is the work done in moving this unit test mass to this point here. Remember, we have moved it from infinity. Now the mathematics involved here, the examiner prevents me from talking about that mathematics, but the gravitational potential at this point here will not actually depend on the distance you have moved from infinity. Mathematicians would, if you have studied integration, I think I would have done this, but I'm not sure if you have studied integration. Because we are integrating from infinity to this point here, then the work done in moving from infinity to this point here, moving a unit mass, that is a mass of 1 kilogram, is what we are calling the gravitational potential. So the gravitational potential is depending on two things. One, it depends on the mass, the large mass actually, because this is a unit mass, which is 1 kilogram. It also depends on the distance from the center of the Earth. Therefore, the gravitational potential is going to be given by a simple expression, which is actually phi is equal to negative gm over r. I want to emphasize that this negative is not optional. Although in finding the force between two masses, it was optional. In finding the gravitational field strength, we consider it being optional. In finding the gravitational potential, which is denoted normal as phi, this is read as phi. In defining gravitational potential phi, this negative here is not optional. Therefore, this negative must always be included in the calculation. So this is what we call the gravitational potential. The work done in moving a unit mass, that is a mass of 1 kilogram, from infinity to a certain point in the gravitational field is the gravitational potential. And this is depending on the mass, and it is also depending on the distance of that mass from, it is actually depending on the large mass, not the smallest mass, because it's 1 kilogram, and it is depending on the distance of that test mass from the center of the large mass. From this expression, since we know that g is the gravitational constant, m is the mass in kilograms, r is radius, so you should be able to establish or to realize the units of gravitational potential. You should be able to realize the units of gravitational potential. I don't know whether, but anyway, this is energy, which is work done moving a unit test mass from infinity to a point in the gravitational field. So work done, that is joules, because we are considering a test mass, that will be joules per kilogram. You can use dimensions and see, or you can use units, deriving units, and see if this comes to this gravitational potential. The work done, that is in joules, in moving a unit test mass, that is a mass of 1 kilogram. So it is the work done per unit mass in bringing a unit test mass from infinity to a point in the gravitational field. So for every 1 kilogram, the work done to move it from infinity to a certain point is what we call the gravitational potential. By the way, potential being work done or energy, gravitational potential is actually a scalar quantity. So from what I have said, I have mentioned the following. Number one, the work done per unit mass in bringing a small test mass from infinity to a point is what we call the gravitational potential at that point. And I have also mentioned that this depends on two important factors, that is the large mass, the mass of the object causing the field, which is in this case is the Earth. It is not depending on the small test mass. After all, it is just 1 kilogram. And number 2, its distance. It is depending on the distance of the test mass from the center of the large mass creating the field. And this gives us an expression that gravitational potential is equal to negative G capital M over R. With the SI units that I have mentioned, joules per kilogram, because it is work done, that is in joules, per unit mass, that is per kilogram. You bring a unit test mass from infinity to a point in the gravitational field. Since this is potential, which is energy, I've also mentioned that gravitational potential is a scalar quantity. Gravitational potential is a scalar quantity. There are a few important points to note. There are a few important points that you should note. Number 1, I want you to note that the minus sign in the equation of gravitational potential is not optional. In force, finding force, we can ignore the negative. By the way, remember the negative in finding the force was emphasizing that the force between the two masses is always attractive. It must always be included, and all values of potential energy in a gravitational field are negative, except at infinity where it is zero. You can't put a negative on zero anyway. By the way, this is not the case with electric fields. When we study electric fields, we shall realize that this is not the case with electric fields. Because we have only positive masses, the force between the two masses is always attractive. I don't think we have negative masses. Now somebody will say, how can a positive mass attract a negative mass? By the way, a charged particle can also have a mass. That is different. But naturally we can't have mass as negative. But a particle which is charged positively, it can also have a mass. So the force between two masses is always attractive. And since the force is always attractive, and potential at infinity is defined to be zero, then elsewhere, gravitational potential will always be negative. But I'm saying this is not the case when it comes to electric fields. Our next unit at school, I think that's when school starts, because I want to stop with the gravitation. Our next unit, which will be electric fields, we shall see that we have repulsive and attractive forces, since we have both positive and negative charges. In electric fields, we shall be dealing with charged particles or charges. And charges can be positive or negative, and the force between charges can be repulsive or attractive. So, in electric fields, sometimes we shall have a negative potential, sometimes we shall have a positive potential. In gravitational fields, we only have negative potential. We shall only have negative potential. So which explanation do we give for this? Why should the minus sign be there? What is the significance of the minus sign? Number 1, we have said potential at infinity is defined to be zero. Potential at infinity is defined to be zero. Number 2, the force between the two masses is always attractive. The force is always attractive. And if the force is always attractive, it means work is done by the test mass as it moves from infinity to a point in the field. Therefore, the test mass loses energy. Or work is gained as we move the object from a certain point to infinity. The object has to gain energy. And if at infinity it is defined to be zero, yet it has to gain energy until it reaches zero, then it should be gaining negative values. Or the values through which it passes should be less than zero. Therefore, the potential be negative. So this is what I've been explaining. The examiner will ask you, explain the significance of the minus sign. Number 1, The gravitational potential at infinity is defined to be zero. We have defined that to be zero. And the force between two masses, or the gravitational force, is always attractive. And if that is true, the force is always attractive, two masses always just attract each other. So you yourself, you are not doing a work when you move one mass towards another mass in the direction of the field. You only do work when you move it against the field. So here in this direction, it is this mass, the one which loses energy. And if it was at infinity when it is zero, when it loses, it means it will now have negative values. So I am saying the test mass moves from infinity towards another mass. Work is done by the test mass. Work is done by the test mass, and as a result, its potential energy decreases. Because when the test mass moves from infinity to a certain point in the gravitational field, it is doing work. So if it is doing work, its potential energy is decreasing. When a stone lands on you, it is because it was doing work as it is falling, so it does work on your head if it lands on your head. So as a result, the potential energy decreases. That means we are getting work out of the system. And if we are getting work out of the system, yet at infinity it was zero, then the potential energy it will have, or the potential it will have, will be negative or less than zero. The potential it will have will be less than zero. So I want you to always remember that when you do work on a body to move it to a higher place, the body gains gravitational potential. However, in the actual sense, the gravitational potential is becoming less negative. So as you move from the Earth's surface, later we are going to see that the potential on the Earth's surface, I think it's negative 63 point something. So as you move out from the Earth's surface, it becomes less negative. In other words, it becomes smaller negative numbers. By the way, it is increasing because negative 2 is greater than negative 4. So until it reaches zero at infinity. So, however, in the actual sense, the gravitational potential is becoming less negative and eventually appears zero. A situation where the gravitational force is acting, there is no gravitational force acting on a body. That is when it is at infinity. So the question will be explain the significance of the negative sign. That will be around 3 or 4 marks. Just to remind you, or just to remind us, let's just have a simple reminder. So the above argument is of course consistent with the electrical course, that is, the electrical case, that is in electric fields. It is consistent. We shall see that when you bring a negative charge towards a positive charge, the potential is going to be negative because the force between them is attractive. And when you bring a positive charge towards a positive charge, actually the potential will be positive because the force between them is repulsive. So we have a negative electric potential when the field is produced by a negative charge, so that the force between the negative field producing charge and the positive test charge is attractive. So when the force is attractive, the potential is going to be negative. And when the field is produced by a positive charge, the potential is going to be positive, because we are going to see that we always imagine bringing a positive charge. So if this is a positive charge, we shall see this in an electric field, and you're bringing a positive charge, then the potential due to this is going to be positive because the force between them is repulsive. When I have a large negative charge and I bring a positive charge, then I'm bringing it in the direction of, actually this, because the force between these two is attractive, then I'm bringing this in the direction of, of the field. Therefore, the potential here is going to be negative. We shall see that in details in electric fields. So here the attractive gravitational force between the field producing mass and the test mass always gives negative potential since the gravitational force is always attractive. So do not forget that in gravitational fields, the force is always attractive, but in electric fields, the force can be attractive or repulsive. The negative sign, the negative sign on or in the equation of electric fields is not optional. It is actually compulsory, even in calculation. So this now reminds me of a graph. Now that we know the expression for gravitational potential, then we can think about a graph. We can think about a graph of gravitational potential with distance from from maybe let me consider the Earth's surface. So we are going to consider the Earth at the center as our central point. When we move, because the graph is the expression for potential phi is given by negative g m over r. So we are considering a unit test mass, a small test mass of 1 kilogram. When I move it away from the Earth's surface, it gains more potential energy. So the graph tends towards the x-axis where potential is 0. At infinity, this graph will touch the x-axis because at at infinity, the potential becomes 0. Remember, I'm considering a unit mass. When I bring this close to the Earth's surface, the potential becomes more negative because the potential decreases. It becomes less than 0. This graph is always and must always be drawn below the x-axis. It must be drawn below the x-axis because the gravitational potential is negative. Reason: the potential at infinity is defined to be 0. The force between two masses is always attractive. So in moving a mass from infinity closer to the Earth's surface, the mass is doing work. Energy is removed from the mass. Its potential energy decreases. So it becomes less than 0, which will be negative. It becomes less than 0, which will be negative. So if the Earth is somewhere here at the center, as I move away from the Earth's surface, tending to infinity, the gravitational field strength weakens. It weakens and weakens. That means when I'm at infinity, the potential energy is going to be 0. But note that you were moving against gravity to reach infinity. So you were doing work. You were adding energy to the system. And energy is being added to the system, but it becomes 0. It means all you were adding was contributing to the negative values. So it was just becoming less negative until it becomes 0. So one important thing that we need to note here is, since the potential is always negative, the graph is normally drawn below the horizontal. It would normally be drawn below the horizontal axis because the potential is always negative. So we have considered a unit test mass to define potential. The work done per unit mass in bringing a small test mass from infinity to a point in the gravitational field of another mass. Suppose now we don't take a unit test mass and we take the whole mass, say 100 kilograms. What will be the work done in moving 100 kilograms from infinity to a point in the gravitational field? Now that will no longer be gravitational potential, but instead to be gravitational potential energy. The work done in bringing the whole mass from infinity to a certain point in the gravitational field will now be the gravitational potential energy. When we consider just a unit mass, then we are referring to the gravitational potential. For the whole object, for the whole mass of the object, then we shall call it the gravitational potential energy. So one important thing we need to remember is that gravitational potential is work done per unit mass, where we were considering 1 kilogram mass. We were considering moving a 1 kilogram mass from infinity. And if the whole body is moved from infinity to a point close to the Earth's surface, that is, the whole mass is moved from infinity. This time we are now not considering 1 kilogram, but the whole entire mass is moved from infinity to a point in the gravitational field. Then the work done to bring the whole object or the whole mass from infinity is no longer the gravitational potential, but it is called the gravitational potential energy. If the work done per unit mass, just 1 unit mass, is given as, if the work done per unit mass is called the gravitational potential, which is negative m times capital M over r, then the work done to bring the whole mass will be, we shall just multiply this by m both sides. So it means the gravitational potential energy, which is written as EP, is going to be equal to the mass times the gravitational potential, which will be negative capital G, capital M, small m over r, where small m is now the mass, the whole mass which is removed from infinity to a point in the gravitational field. So for a body of mass m, its gravitational potential energy will simply be the gravitational potential times the mass of the body. Gravitational potential multiplied by the mass of the object. I want you to note very carefully that even here, the minus on potential energy is not optional. The minus sign on potential energy is not optional. It is actually compulsory. The minus sign on potential energy is not optional. So if we are considering the Earth's surface, this will be the mass of the Earth, this will be the mass of the test mass, or it will be the test mass, and r will be the radius of the Earth. That is, if the mass is moved from infinity to a point on the Earth's surface. So this will be the radius of the Earth. We can even establish the potential on the Earth's surface, but that's not my major concern for now. So I have said for a body of mass m, its gravitational potential energy will be m times as larger as for a body of a unit mass. Note that for a body of a unit mass, it was negative g m over r. So for a body of a mass m, its gravitational potential energy will be that mass times the gravitational potential, where the gravitational potential is given as phi, so the potential energy will be negative G capital M over R. I will not, there's no need of actually deriving that expression because it is direct. If we are considering the Earth's surface, or the surface of the Earth, where R is going to be the radius of the Earth represented by RE, so this will be just radius of the Earth. Points to note, important points that we need to note. Note the following. Number one, the negative sign, the minus sign is first of all not optional, even in calculation. The negative sign is not going to be optional, even in calculation. What is the significance of the minus sign? The negative sign implies that the potential at infinity, first of all, is zero and is greater than the potential at any point closer to the Earth's surface. Why? Because one, the force between the Earth's surface and any mass is attractive. In moving an object from infinity closer to the Earth's surface, the object is losing energy. The object's potential energy decreases. Work is done by the object. Therefore, the potential energy must be negative. So, number two, the decrease in potential energy as the mass moves in from infinity towards the Earth implies that work done by the gravitational force of the Earth on the mass m is positive. What does that mean? When I move a mass to infinity, the work done on the mass by the gravitational force which is pulling it closer, is going to be positive. So if you try to subtract between two energy levels, you'll get a negative difference, which is going to be the work done. If I move an object from a point A away from the Earth's surface, where this is the Earth's surface, to point B, note that the potential here is less than the potential here. The work done to move from A to B is the difference between the two potentials times the mass of the object, as we are going to see. And this work done will be positive, of course. When you get the higher potential energy minus the lower potential energy or potential, the difference is a positive number. That's what we mean by that. For example, if here we are close to the Earth's surface and this is negative 70, and we move far away, this becomes negative, say, 30, because it becomes less negative. The work done to move from A to B is going to be determined by the difference in the potentials, and the difference in potential is negative 30 minus negative 70, which is positive 40. So that's what I'm meaning, that the work done by the gravitational force of the Earth on a mass m is positive as you move a mass towards infinity. Okay, so when an object is within the gravitational field of a planet, it has a negative amount of gravitational potential. It also has a negative amount of gravitational potential energy as measured relative to infinity. Infinity is now a better reference point. And we have also said that the amount of potential energy or gravitational potential energy is depending on two things. Number one, the mass of the object, that is the mass of the planet, the large mass, the largest or the bigger mass creating the resultant field. And number two, the distance between the centers of the mass of the object and that of the planet. Now this is the small object and the other one is the planet. So for the mass of the object, we call it small m, and the mass of the planet, assuming the planet is massive, we call it capital M. So it also depends on the distance between these two masses. As we have seen, potential energy EP is equal to mass times potential, which is equal to negative G capital M times small m over R. I am certain many people will square this because they are now used to Newton's law of gravitation, but gravitational potential energy is not squared. Okay, last point here. Potential, like a field strength, is a property of the field at a point and is independent of the object placed there. We have seen that potential was Gm over R. It was independent of the object placed there. Two objects with different masses at the same point in the field are subject to the same potential, but they have different potential energies. They are subject to the same potential if they are at the same distance from the Earth. So if I have here two objects, if this is the Earth's surface, and I have two objects at this point here, object A and object B. If this is 2 kilograms and this is 7 kilograms, if I consider potential at this point for both objects, potential is the same because it is not depending on these masses, it is only depending on the mass of the Earth. It is only depending on the mass of the Earth. So potential is not the same. Potential is the same, but potential energy is depending on their masses. So potential energy will be different. So two objects will have the same potential if they are at the same point, but they will not have the same potential energy because potential energy depends on their mass, but potential does not depend on their mass. So let's now try to picture, we are going to picture a spacecraft or a spaceship which is coming from a very distant star to visit our solar system. How does its gravitational potential vary as it moves along its path? Let's say at one point it comes, of course it will come, let's say it comes closer to the sun before it tends to come closer to the earth. If it is coming from infinity, its potential energy is going to be zero from infinity, or coming from infinity, since we cannot exactly define where infinity is, or the distance infinity is, or the distance called infinity, then we may not actually draw a graph touching the x-axis, but we know it tends towards the x-axis. Note that this is always going to be negative, so the graphs are going to be below the x-axis. So this is what we are saying. Let us picture a spacecraft or a spaceship that is coming from a distant star. When I talk about distant star, it is coming from infinity. Of course, as it comes from infinity, it will first come closer to the sun. And if it comes closer to the sun, after then it moves away from the sun, it will now come, let's say, closer to the earth. How does the graph of gravitational potential vary with its movement? So this is what we are actually talking about. When it is coming from infinity, at infinity its potential is almost zero. But as it comes closer to the sun, the potential becomes more negative. It becomes more negative. If it moves away from the sun, the potential becomes less negative. Therefore, the graph tends towards the x-axis. Remember, potential is equal to negative Gm over R. While at infinity, the potential is close to zero. When closer to the mass, the potential becomes more negative. And as you move away from the sun, the potential now increases because it is tending towards zero. It becomes less negative and tends towards zero. But before it becomes zero, because it will not have reached infinity away from the sun, it is now getting closer to the earth. Again, the potential becomes more negative. That is, the potential decreases. That's why you see the graph is turning towards the Earth's surface and it is moving out from the x-axis because the potential decreases. It becomes more negative. Again, as it moves away from the Earth, the potential becomes less negative. Now you may be wondering, why is it that? Why is it that this graph here, the change in potential here, you can see the change in potential here. This change in potential here for the sun is not the same as the change in potential here for the earth. Note that the potential is depending on the large mass creating the field. And we know that the mass of the sun is approximately 2.0 times 10 power 30 kilograms. And the mass of the earth is approximately 6.0 times 10 power 24 kilograms. What does that mean? The sun creates a deeper potential well than the earth. So we expect the change in potential to be greater for the sun compared to the change in potential for the earth. For any other planet which is less massive than the sun, than the earth, its potential well will also be smaller. That's why you notice the change in potential here for the sun is greater than the change in potential here for the earth. I want you to note that these graphs or this graph will be below the x-axis. You are going to realize when we look at the past paper questions that most of the questions are graphs, and that's what makes this a little bit complex. Most of the questions will be graphs. At this point, you must even have started opening the questions to see what is enclosed in there. Most of the questions are actually graphs. So let's try to give an explanation to these two graphs. Let's concentrate on at least three parts of the journey of the spacecraft. Number one, as the spacecraft approaches the Earth, maybe from the other side, it is attracted towards the Earth. So the closer it gets to the Earth, the lower its gravitational potential becomes. That's why you see it becomes more negative. So it means it has a lower potential when it gets closer to the Earth. If it moves away from the Earth towards the Sun, as it moves from the Earth it has to work against the pull. Here it is doing work against the pull of the earth. But then it reaches here at this point here, it reaches a certain point in between, now where it is moving towards the sun, then it means energy is being lost from it because it is now going to be moving in the same direction as the gravitational pull due to the sun. Note that the sun is very massive, therefore it creates a very large field compared to the earth. Therefore, it creates a giant potential well. We call it a potential well. That is a great change in potential. So it will create a giant potential well. And remember, for us, we live at actually the bottom of this potential well because we live just close to the surface or just on the surface of the earth. So as the mass approaches the sun, it is now attracted towards the sun. So it is attracted towards a much deeper well than the earth. Because the sun's mass is very great compared to that of the earth, so its pull is much stronger than that of the sun, and therefore the potential at the surface of the sun is much more negative than the potential on the surface of the earth. All that being said, we qualify for examples. But before we qualify for examples, this is a simple explanation. So I have said uh, as the spacecraft or the craft approaches the Earth, it's attracted towards the Earth. So it means the closer it gets to the Earth, the lower its gravitational potential energy or the lower its potential. Then now it moves away from the Earth. As it moves away from the Earth, it has to work against the pull of the Earth. So it loses its what? Actually, it gains potential energy when it is moving against. So the gravitational potential energy increases. And so we can say that the potential also increases as you move away from the large mass. Because tending to infinity, where infinity has a higher potential energy, which is zero, it means the potential becomes less negative. We say the Earth's gravitational field creates what we call a giant potential well, and for us, we live at the bottom of the potential well. As you move away from the Earth's surface, the potential well becomes less strong. And as it approaches the sun, it is attracted into a much deeper, this is much deeper than that of the earth. The sun's mass is much greater than the earth's, and so its pull is much stronger. And the potential in the surface of the sun is more negative compared to that of the earth. Examples. Examples. So for energy in a gravitational field, we have almost exhausted it. We are only remaining with energy of satellites, as we shall see. Examples. Number one, how much work is done by the gravitational field in moving a mass of 2.0 kilograms from infinity, remember at infinity potential is zero, to a point A 0.4 meters from the mass m of 30 kilograms. So we are going to assume that the mass of 30 kilograms is the one creating the field because it is more massive than the other one of 2 kilograms. So maybe I can put this in drawing. Let this be the mass of 30 kilograms. So this will be the large mass. So we are assuming we have moved a small test mass of 2.0 kilograms from infinity to a point which is at a distance of 0.4 meters. So we want to find how much work is done, that is the gravitational potential energy if I consider the whole mass. It is gravitational potential if I consider just 1 kilogram. So the work done, which is equal to the potential energy, is going to be equal to the mass times the potential. So this will be equal to the mass times capital G times capital M divided by R, but remember this must be potential is negative because we are moving from infinity where potential is zero. So this will be equal to a negative 2 times 6.67 times 10 power negative 11 multiply this by the large mass, which is 30, divide by the distance, which is 0.4. And when I press my calculator, so I am getting negative 1.0 times 10 power negative 8 joules. So it means this is the work which must be, or which would be done by an external force, and this work is negative. So the work done by the field is positive. That means the work done by the field will be actually positive if the work done by an external field is negative. So we have used 6.67, we have used 30 as the larger mass, and we have used 0.40 as the distance between the large mass and the small mass. Okay, example number 2. Example number 2. I hope it is example number 2. What is the gravitational potential energy of a 60 kilogram student on the surface of the Earth? What is the gravitational potential energy of a 60 kilogram student on the surface of the Earth? Now, very first, you will think it is zero, because you have already thought that when you are standing on the Earth's surface, potential energy is zero. Now, I want to let you know that potential energy is not zero on the Earth's surface, because with reference to infinity, potential energy is zero at infinity. When infinity is the reference point, potential energy on the Earth's surface is not zero. If you are standing on the Earth's surface, you are somewhere here, a small mass of you is standing somewhere there, which is 60 kilograms on the Earth's surface. What is the gravitational potential energy on the Earth's surface? We imagine moving you from infinity to the surface of the Earth, where you will be at a distance which is equal to the radius of the Earth. The radius of the Earth is 6.4 times 10 power 6 in meters. So the gravitational potential energy, which I will call EP, is going to be the mass times the potential on the surface of the Earth, which will be negative the mass times capital G times the mass of the Earth over R. Now I'm substituting. This will be negative 60 times 6.67 times 10 power negative 11 times. The mass of the Earth is 6.0 times 10 power 24. That constant should always be given. Now your distance from the center of the Earth is going to be 6.4 times 10 power 6. I'll press my calculator. You can also press yours as a way of verifying, because I should always be able to make mistakes. After all, with an excuse that I'm human. So, pressing my calculator here. Okay, so this is going to be equal to negative 3.8 times 10 power 9 joules. So it means to get the student away from the Earth's surface, so that the student reaches infinity where the gravitational potential energy is zero, the student will need 3.8 times 10 power 9 joules to reach infinity. The student, it will need 3.8 times 10 power 9 joules of energy to send this student from the Earth's surface to infinity where potential energy becomes zero. I think that is obviously easy and understandable. Number 3, what is the potential? Oh, I think there was another part of the question. I didn't notice it. What then is the minimum energy that would be required to get this student completely out of the Earth's gravitational field? I think I've mentioned the minimum energy will be 3.8 times 10 power 9 joules to reach infinity, because at infinity potential energy is 0. So the potential, this should become less negative until it reaches 0. So it means it will change from this to 0. So that means we get 0 minus this, which gives us this value here. The student will need this to reach infinity, or to be free from the Earth's gravitational field. Okay, going back to number 3. What is the potential you experience at the surface of the Earth? How would the answer be different if your friend who weighs more than you worked it out? What is the potential you experience on the surface of the Earth? And how would the answer be different if your friend who weighs more than you worked it out? First of all, let's find the potential on the surface of the Earth. We have said the potential is the work done in moving a unit test mass, or a mass of 1 kilogram, from infinity to a point in the gravitational field, which would be negative g capital M over R. This would be negative 6.67 times 10 power negative 11 times 6.0 times 10 power 24 divided by 6.4 times 10 power 6. And this would be negative, because it must be negative. So I am getting negative 63 times 10 power 6 joules per kilogram. So this is going to be negative 63 megajoules per kilogram. So how would the answer be different if your friend who weighs more than you worked it out? Earlier on we said the potential does not depend on the mass of any of you. It will depend on the mass of the large object creating the field. And therefore it means your potential will be the same as your friend's potential if you are at the same point on the Earth's surface. So I am saying to answer that question, the answer is going to be the same for everyone. Potential is a property of the field, and all objects at the same point in the field are subject to the same potential. Remember, here we consider the 1 kilogram of a substance. Some people don't know that 1 kilogram of feathers weighs the same as 1 kilogram of stones. That one I'm very sure. But potential is a property of the field, and all objects at the same point in the field are subject to the same potential. But remember, the potential energy will be different, because for potential energy, multiply potential with the total mass. For potential energy, multiply the potential with total mass of that object. Okay, example number 4. Example number 4. What is the potential at a height of 36,000 kilometers from the Earth's surface? This is the height of a geostationary orbit. If you remember geostationary satellites or geostationary orbits, normally this is the height of a geostationary orbit. What is the potential difference between the surface of the Earth and the geostationary orbit height? So what minimum energy is required to launch a 150 kilogram satellite into geostationary orbit? Why is the actual value a lot more? Why would the actual value be actually more? Let's begin by finding the potential at that height. Potential at that height, remember we are measuring it, this is the height from the surface of the Earth. Yet potential is measured from the center. So if this is, let me say this is the Earth. I know so many people believe that when we talk about height, it is always just above in the vertical plane. But height with the Earth as the reference point, height could be this side. So this height is 36,000 kilometers. But remember, potential is measured right from the center of the Earth, where this distance is 6.4 times 10 power 6 in meters. So we want potential at this point here. Of course, we must include the potential at the surface of the Earth. So potential at that height is going to be negative capital G capital M over R, which will be negative 6.67 times 10 power negative 11 times the mass of the Earth, which is 6.0 times 10 power 24, divided by R will be this distance plus this distance. So this will be 6.4 times 10 power 6 plus 3.6 times 10 power, this is 3, 4 times 1000, that is power 7. I press my calculator. So I am getting negative 9.4 times 10 power 6 joules per kilogram. By the way, I'm putting joules per kilogram for potential, but potential energy is still joules because you multiply by the mass in kilograms. So the per kilogram cancels out. Oh, I would just quote this in megajoules as negative 9.4 megajoules per kilogram. So that is the potential at that height. This is the height of a gestational orbit. What's the potential difference between the surface of the Earth and geostationary orbit height? What is the potential difference? Of course, we have already, in the previous example, we have obtained that the potential on the Earth's surface, was approximately negative 63 megajoules per kilogram. Then the potential at that height is this. So the question is, what is the difference? By the way, I think this is, did I press my calculator wrongly? 6.67 exponent negative 11, 6.0 exponent 24 divided by 6.4 exponent 6 plus 3.6 exponent 7. 9.4 times 10 power 3, no, yeah, power 6. 9.4, yeah, times 10 power 6. So this, we want the difference in potential. So difference in potential is going to be, because this is higher than this is at a higher height, so it is higher. So we shall say negative 9.4 minus negative 63. And this is giving me, this is positive 53 megajoules per kilogram. So it means you must add 53 megajoules per kilogram onto 90, onto negative 63 megajoules to reach the height of um, to reach a height of 36,000 kilometers. So what is the potential difference between the surface of the Earth and the gestational orbit? That one we have finished. So what minimum energy is required to launch a 150 kilogram satellite into geostationary orbit? Why is the actual value a lot? So what minimum energy is required to launch a 150 kilogram satellite into gestational orbit? I want you to note that the potential difference has been obtained to be positive. What does that mean? It indicates that to get to a geostationary height, a larger amount of energy would be required, which is approximately 53 megajoules per kilogram. So there is no problem. There is nothing like potential. There is no problem with the potential difference being negative. It doesn't change the potentials themselves. The potentials themselves are negative, but the potential difference can be positive. And of course, even the potential energy the change in potential energy can be positive, even though the potential energies themselves are positive. Earlier on, we have already known that the potential difference between the Earth's surface and the gestational orbit is actually this value here, which we have calculated, and it is positive. So it means for 1 kilogram, we need this energy to take it to from the Earth's surface to this height here for every kilogram. Now we have 150 kilograms. So what we are actually calculating is potential energy, or the change or the gain in potential energy. So the gain in potential energy, E delta P, is going to be equal to the mass times the change in potential, which will be 150 kilograms times 53 megajoules per kilogram, where this one has cancelled. Pressing my calculator, 3 times 150. So I'm getting 7950 megajoules. This is 7950 megajoules. Or I will round off this to 1, 2, 3. That will be 80 gigajoules. Not 80, it is 8.0. 1, 2, 3. That is 8.0 gigajoules. So it means I will require that amount of energy to launch the satellite from the Earth's surface to that geostationary orbit. However, the last question is saying, why is the actual value a lot more? This is what I expect by calculation. But the actual value to reach this point could be a lot more, because as the satellite is moving, remember there is air resistance. So if you give it exactly this amount of energy and there is air resistance, part of this is going to be used to do work against air resistance. That means the balance which is remaining will not be enough to take it up to the geostationary orbit. So you must give it an energy which is greater than this. We are considering this if and only if all other factors do not affect the motion of the satellite. So I'm saying, actually, much more energy is required because there is a drag or friction drag or viscous drag. There is drag, that is a friction force. Drag with the Earth's atmosphere to overcome on the way up. There is drag with the Earth's atmosphere to be overcome on the way up. So it means we need to give our satellite more energy slightly less than this. This is the minimum to put it to that orbit. But if we give it exactly this, we have assumed that there is no drag. Otherwise, if we know that there is drag or frictional force or air resistance as it is moving, then we must give it more energy slightly above this to compensate for that which will be lost in doing work against friction. By the way, also the rockets themselves have mass, or even the satellites themselves also have mass to be lifted into orbit. Because if a satellite is launched with those, we call them thruster rockets, which help it in preventing it falling off its orbit by being fired off, because they fire off thrust rockets, which propel them forward to give satellites more speed. It means the answer we have arrived at here is only the energy required to lift the satellite against the gravitational pull of the Earth, because the rockets themselves which are attached to the satellite also have mass, which must be lifted into the geostationary orbit. But the most direct answer here is relying on the drag force with the atmosphere of the Earth as the satellite is moving upwards. Okay, I think I've tried to give a simple explanation to that. Example number 5. Can't I make this the last example? I think this should be the last of the last examples. Example number 5. What is the potential difference between the top and the bottom of an office block on the surface of the Earth that has a height of 50 meters? This is close to the surface of the Earth. The field is roughly uniform, so you can always use simple equations for change in gravitational potential or change in potential. What minimum energy do you use in walking up to the top of the building? That is now the question. What is the potential difference between the top of an office block on the surface of the Earth that has a height of 50 meters? Now, I want us to use two expressions and see that um, this could be almost the same if we use the infinity as the reference point. But let's check. So since we are close to the Earth's surface, then the change in gravitational potential or the difference in potential, no, this is potential energy. I want potential. So the change in potential this time will simply be G times H. That is the gravitational field strength times the height, which will simply be 9.8 times 50, which when I press the calculator, I can't multiply this by mass because this will mean I'm finding potential energy. Yet I have to consider 1 kilogram. Or if you want, you can say times mass, but note that for potential it is per unit kilogram. So this will be equal to 490 joules for every kilogram. Maybe you may want to use this expression here. Delta phi is equal to the negative m times, okay, negative, not m, the negative G capital M over R. Now this will be negative. I'm now considering this. By the way, this was change in height. I will say delta H. So I'm now considering this to be, I'm looking at a height of 50 meters. So this will be a negative 6.67 times 10 power negative 11. Now I'm considering the mass of the Earth, which is 6.0 times 10 power 24. Divide by, now this distance here is going to be the radius of the Earth plus the height. So that would be 6.4 times 10 power 6 plus 50. So let us see what happens. 6.67 exponent negative 11 times 6 exponent 24 divided by 6.4 exponent 6 plus 50. So I am getting the potential at that height. Let this not be change in potential. I want it to be just the potential at that height. So the potential at that height is actually equaling to 6.62 6.25 times 10 power. This is 1, 2, 3, 4, 5, 6, 7 times 10 power 7, which is approximately 62.5 times 10 power 6, which is approximately 62.5 megajoules megajoules per kilogram. That is the potential at that height. Now, if I want the change in potential on the surface of the Earth, the potential is approximately on the surface of the Earth, the potential is approximately 63, I think. By the way, this was negative. The potential is approximately 63. So we can get the difference here. We can get the difference here. So the change in potential is going to be equal to, so we are saying the change in potential on the Earth's surface is around negative 63. So this will be negative 62.5 minus negative 63. Remember, this is in mega joules per kilogram. Let's find the difference. 62.5 minus 63, or 62.5 plus 63. So I am getting the change in potential here as being equal to 0.5 megajoules per kilogram. And this is the same as okay. So I wanted actually to let you know that you must have realized, let me just maintain the same number of significant figures here for uniformity. For uniformity here, let me have the same number of significant figures so that this will round off to approximately 63. This will round off to approximately 63. So this will be approximately negative 63 minus negative that. This will be approximately 0. So I wanted to show you that if with using the infinity as the reference point, close to the Earth's surface, if the change in height is very small, you notice that the change in potential energy is approximately 0. That means your weight will not change significantly when you move from just the surface of the Earth to a certain height. But that does not mean that there is no change in potential. This change in potential with infinity as the reference point is very, very. So if with infinity as the reference point, the change in potential when you move to a certain height of 50 meters, for example, is the change in potential is very, very small and almost negligible. But it doesn't mean that there is no change in potential. That's why I'm saying for points close to the Earth's surface, then the change in potential can be considered to be equal to the gravitational field strength times the change in height. Because close to the Earth's surface, G is almost constant. So the question was saying, what minimum energy do you use in walking up to the top of the building? So the minimum energy then, that would be the potential energy, which is the work done. That would be the mass times the change in potential. This will be equal to the mass. You can estimate your mass. Let's say you are 70 kilograms times the change in potential, which is approximately 490. If I'm using this as a reference, the Earth as a reference point. In this case, you will need about, pressing my calculator, 7 times 49, 2.9 times 10 power 4 joules, around 2.9 times 10 power 4 joules. So I want you to know that actually you may need more energy than 2.9 times 10 power 4 joules to climb up to the top of the building, because your body may not be actually efficient and your body may warm up as you are climbing the stairs. That means you may need more energy actually in climbing to the top of the building. So such other factors, this is going to be the minimum energy you need to do against, or the minimum energy required against gravity to move up to the what? The top, up to the top floor, or at 50 to a height of 50 meters. But the truth is, you will need more energy, since some of this is going to be wasted in warming up your body as you climb up, because the body is not efficient. I think I've tried to give some examples. This could be, I don't know whether this could be harder than the ones you'll find in the past paper questions, but you'll see yourself. Self-check. Self-check, I think this is self-check number 5. Self-check number 5. Now this could be general. The Earth has a mass of that. We are now familiar with the mass of the Earth, and of course we shall use it every time, but many times it is going to be given in the list of constants. So the Earth has that mass and that radius. Find a change in gravitational potential energy of a meteorite of mass 150 as it moves from infinite distance to the Earth's surface. So here it is moving from infinity. The meteorite starts from rest. That means its initial velocity is 0. With what speed does it strike the Earth? So the loss in gravitational potential energy as it leaves infinity should be the gain in kinetic energy. Number 2, the Earth's radius is about that. The acceleration of free fall on the Earth's surface is about 9.8. G is that value. Use this information to estimate the mean density of the Earth. Use this value to estimate the mean density of the Earth. I think using this value will just be finding the mass of the Earth. Then using this radius to find the volume, you can estimate the mean density. Number 3, the times for Mars and Jupiter to orbit the Sun are 687 and 4330 days respectively. The radius of the orbit of Mars is this, calculate the radius of orbit of Jupiter. Here you can just use t squared is equal to a constant times r cubed, because they are both orbiting the same center, so it means the constant k is the same for both. You just solve the two equations. Number 4, the radius of the Earth is again given as that, and the gravitational field strength at its surface is 10 newtons per kilogram. At what height above the surface of the Earth is the gravitational field strength equal to that? Of course, here I just rely on the expression of gravitational field strength. We have seen gravitational field strength is equal to capital G m over r squared. So you have G on a certain on the Earth, you have G on G at a certain height. So you have two equations, and you'll be able to find the height. Remember, r is always measured from the center, and the height will be the radius, the distance from to the center minus the radius of the Earth. Then you have two 2.5 kilogram masses are placed with their centers 10 centimeters apart. Calculate the size of the force. That is easy. Newton's law of gravitation. Then the mass of the moon is that, and its radius is that. Use the value of G above to calculate the value of free fall on the moon. Of course, G is 6.67 times 10 power negative 11. That is newtons meter squared per kilogram squared. The asteroid Ceres has a diameter of 785 kilometers and a mass of 1.0 times 10 power 20 kilograms. Calculate the field strength and the gravitational potential at the surface. So that is self-check. I think that is enough for self-check number 5. I beg to stop here for now, and I hope this sounds to be helpful. At this point, you should now begin going, if you have extra free time, you should be beginning to go through your past paper questions of gravitation. Thank you and see you. Bye bye.